In the last video, we defined the sine and cosine trigonometric functions. Well, there's a third trigonometric function that is well known and often used, tangent, and that's exactly what we're going to be focusing on in this video, the tangent trigonometric function. So let's use the unit circle just as we did in the previous video to define sine and cosine. Let's use that unit circle to define tangent, which is often simply abbreviated to tan. So we have a circle here in our whiteboard, and if I was to draw a radial line on that circle, and we mark this with a value of 1, so the radius is 1 unit, we know therefore this circle is a unit circle, and we saw that any point on that circle has the coordinates x, y, and in the previous video we saw that we can define the coordinates of that point, if you will, or more accurately define the sine and cosine trigonometric functions based on the coordinates of that point by looking at the rotation of a line around the circle in the anti-clockwise direction from the x-axis. That rotation of theta means that our cosine of theta is equal to the x-coordinate and our sine of theta is equal to the y-coordinate. Now, interestingly, we can actually relate these values to the lengths of the edges of a right-angled triangle. If I constructed a right-angled triangle between our point xy and the origin of our circle, something that we've done quite a lot in volume 1 when we were dealing with the equation of a circle, if I was to construct a right-angled triangle, we know that travelling from a value of 0 in y up to our y-coordinate in y, we know that that must be a distance of sine theta. So I can say that this edge, this particular edge, I'm simply just going to call it sine. And we know that travelling from 0 to our x-coordinate in x, well, that distance must be cosine of our angle. I'm just going to simply label this as cos. Now I need to make a little bit more room here, so I'm going to erase our workings on the right hand side, because all that's important at this point now is our right-angled triangle. So here we have a right-angled triangle. We know the hypotenuse of that triangle has a length of 1, it is our radius, and we know that the base of the triangle travelling in x is a length of our cosine theta, and the height of the triangle in y, if you will, is a length of sine theta. And I want to label the vertices of this triangle, and I'm going to label them as A, B, and C. Well, what if we took this right-angled triangle, and what if we scaled it up uniformly? So we maintain the ratios between these three edges. Well, we could scale it up so that the edge that's lying on the x-axis is a length of 1 unit long. In other words, we scale it up so that our point C sits here on our circle. So we're going to be scaling it up uniformly so that we have a point that sat on our circle, and we can label that point, I'm going to label it E, and where point D is going to become apparent in a second. So if we had that point E, well, we know therefore the side of our triangle is going to extend upwards, and it's going to extend upwards to a scaled version of our radial line. So our radial line is going to travel in the same direction, and the side of our triangle will travel straight upwards to meet with that line. And our point D is actually the point where they meet. So before anyone wonders where D disappeared to and I labelled someone E, that's where D is. Here's this point here. Why am I labelling them in that order? Just to follow with the notes that I have here so I don't confuse myself. So we have another right-angled triangle here, and it's a uniformly scaled version of our original triangle ABC. Now notice this new edge, ED, this edge right here, is actually the tangent to our circle at point E. If it was extended to an infinitely long line, it would only touch the circle at one point. That point would be E, and it's perpendicular to AE, and by very definition, because it's perpendicular to AE, which is a radial line, if you will, of our circle, then by very definition the line ED is a tangent to our circle. Therefore, the trigonometric function tangent can be defined as the length of this line ED. So I'm going to label this edge of the triangle as tan. But how can we find out the length of this line? Well, actually, that's quite easy. Because our bigger triangle, our scaled triangle ADE, is a uniformly scaled version of ABC, we know that the relative proportions of each of the edges are the same. That is to say, if we scaled AC, our edge here, if we scaled that up by 2 to get AE, then we'd have to scale BC up by 2 to get DE. The proportions between the edges in our first triangle, those proportions are the same as the edges in our second triangle. And we can actually write this relationship as a ratio between two pairs of edges. And as an aside, this is one of the relationships known to be true between what are known as similar triangles. Triangles that are simply a uniformly scaled version of one another. So this relationship, if you will, states that ED divided by EA or AE, so this edge divided by this edge, that ratio between those two edges is going to be the same as this edge divided by AC. So the same edges, but in the other triangle, the ratio between them is the same. So it's going to be equal to CB divided by AC. So we know that the ratio between our edge that runs in X to the edge that runs in Y, that ratio for each triangle, because they're scaled versions of one another, that ratio is the same. But we actually know quite a lot of information for these edges. We know, firstly, that EA or AE, that is a radius line, and our radius is 1. So that means that EA is actually a value of 1 unit. And we know that anything divided by 1 is simply itself. So that means this divide disappears. So ED is equal to CB over AC. Well, ED is our tan of theta. So ED is our tan of theta. CB, this edge here, is our sine of theta. So CB is our sine of theta. And AC is our cosine of theta. So if we replace all that information, we can see that the tan of theta, the tangent of theta, is equal to the sine of theta over the cosine of theta. And that's the very definition of tangent. It is defined as the relationship between sine and cosine. Tan of theta is equal to sine theta over cos theta. That is the definition of tangent. So as we think of how tangent's going to change when our angle changes, we can see that as theta increases, well, starting out, when theta is equal to 0, the length of our tangent is going to be equal to 0. This edge here, when our angle is 0, is going to be nothing. We're going to have a length of 0. But as theta increases, tan of theta is going to increase slowly at first, then more and more and more quickly. However, notice that when our angle becomes 90 degrees, meaning that the line AD is pointing straight up, well, we know that ED, this tangent line, is always vertical. It's always going to be from this point E on our circle pointing vertically up. Well, what do we know about that? If we have a vertical line here at point E and another vertical line here at the origin, those two lines, because they're both vertical, they're both travelling in the direction of our y-axis, they're parallel to one another. And that means they can never touch. The problem there, of course, is that we're trying to form a triangle. We've got AD pointing up here and ED pointing over here. They need to form a triangle, but they're parallel. They're never going to intersect. And what that means is that this edge, ED, becomes infinitely long. It doesn't matter how far it travels for, it'll never form a triangle. What we know from this, therefore, is that the tan of 90 degrees, or pi over 2 radians, the tan of 90 degrees is infinity. Now, as we continue past 90 degrees, we can see that, indeed, our tangent should then decrease again. But we need to be careful here, because Notice what happens to our value of sine and cosine once we pass that 90 degrees point. Well, the sine, which is equal to, remember, y is equal to the sine of theta, x is equal to the cosine of theta. Our sine stays positive. We pass that 90 degree point, y is still positive, sine is still positive. But when we pass that 90 degree point, look what happens to our cosine. It's equal to x, which goes from being positive to being negative. So as we pass that 90 degree point, we've got a positive value divided by a negative value. That gives us a negative value. So even though at 90 degrees we hit infinity, and as we pass round we're going to have to come back down, if you will, from infinity, what actually happens is as we just pass 90 degrees, we jump from positive infinity to a tangent of negative infinity. So what this tells us is, in terms of our diagram, the length of the edge ED simply tells us the magnitude of the value of tan theta. It tells us how large it is. It doesn't tell us whether that value is positive or negative. To find that out, we must look at whether sine and cosine are positive and negative and see how that affects the value of tangent. So in this case, we've seen that we get a negative tangent once we cross 90 degrees, and that means that instead of decreasing from infinity once we get to 90 degrees, really, tan of theta is increasing from negative infinity. And that's going to be rapidly at first, but as we reach 180 degrees or pi, that change is going to slow down, and once we actually reach 180 degrees, we know that our tan of theta, because the line AD here is going to be pointing straight out horizontally, we know tan of theta is going to be a value of 0. Then as we continue increasing from 180 degrees through to 270 degrees, or 3 pi over 2 radians, notice in this quadrant, both sine and cosine are negative. That means we take a negative value, we divide it by another negative value. Those negatives cancel to give us a positive value. Our tangent in this third quadrant is positive. And because tangent is positive, it means that we've been increasing from negative infinity slowly at first, then quicker and quicker and quicker. We reach 0. Quickly at first, then more and more and more slowly, we reach 0, and then we start to increase from 0 again, slowly at first, then quicker, 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 until we reach 270 degrees, and at 270 degrees, notice what happens. We have another situation where the edge AD is vertical, and ED would be vertical. That means they're parallel, that means they never touch, and that means the tan of theta becomes infinitely big again. So we're infinitely big up here, we suddenly jump to negative infinity, then we increase quickly, 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 slowly, reach 0, then we continue increasing slowly, 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 then more quickly until we hit a positive infinity again. Notice what happens as we just cross 270 degrees and into the fourth quadrant. We know that our sine here is negative still, because y is negative, but our cosine is positive. That means we have negative divided by positive. That gives us a negative tangent. So once again, we've jumped from positive infinity to negative infinity. And as we change from negative infinity through from 270 degrees to 360 degrees, or 3 pi over 2 to 2 pi, as we change, we're going to jump to negative infinity, then increase quickly at first, slowing down until once again at 360 degrees, we reach a value of 0 for tangents. It's quite a mouthful, and it's going to be a little hard just to hear what's going on from my speaking. So really what we need to do is graph this, but I did want to be able to doodle all over our unit circle whilst explaining what's happening to tangent. We can now go back, recap this and graph it, and you're going to see a lot more clearly what is going on with the tan of theta as we rotate around our unit circle. Now you will notice that it's periodic again. As we rotate past 360 degrees and keep going, the tan of theta, that pattern is going to repeat. But unlike sine and cosine, we don't have a minimum value of -1 and a maximum value of +1. We have a minimum value of negative infinity and a maximum value of positive infinity. So let's go ahead and plot tan of theta on a graph. So much like our sine and cosine graphs. So here's our horizontal axis, and this is theta. And I'm going to plot the graph not to be confused with y equal to sine theta. I'm going to plot the graph of y is equal to tan theta. That does not mean that tan theta is defined as y of the point of our coordinate, not at all. It means just in this graph that my y-axis is going to give me a curve, an equation that is y is equal to tan of theta. So please bear this in mind. I'm only using y here so that we have a variable that we could map a graph onto this particular set of axes. It does not in any way bear any relation to y is equal to sine theta, which is how we define sine theta with regards to the point on the circle. So just wanted to clear that up. So really all I'm doing is setting a y coordinate equal to a tan of a theta coordinate to enable me to graph our tan theta. So I need to, starting at 0, we know we go up to positive infinity down to negative infinity, so I'm not even going to worry about putting measurements on our y-axis. And I know that I need to go at least up to 2 pi, so let's say this is 180 degrees or pi, and let's say this is 360 degrees or 2 pi. It's going to be useful to know our 90 and our 270. And again, just to help sink this all in, that's pi over 2 and 3 pi over 2. So starting out with a theta of 0, we know that our tan of theta is 0 because our length of our line ED is 0. So at 0, tan of theta is 0. And we saw as we increase towards 90 degrees, slowly at first, then more and more and more rapidly, tan of theta increases, but at 90 degrees, tan of theta is equal to infinity. And that means, really, we're never going to touch a point on this graph. So we can, I'm not going to get too into detail on what this means, but it's quite common when we have a graph that will extend up to infinity, it never quite touches a point on the graph. It's quite common to show that with a dotted line. So we have a dotted line through 90 degrees, starting out at 0 when theta equals 0. We increase slowly at first, then more and more and more rapidly, but we never actually hit infinity, or rather, never actually hit a value on our graph because we hit infinity when we hit 90. So slowly at first, more and more quickly, and then upwards towards infinity and off of the range of our graph. We said that once we pass 90 degrees, because in this quadrant our sine is still positive, but our cosine is negative, sine over cosine becomes negative, our tan becomes negative, and we jump to a negative infinity. So as we pass 90 degrees, we jump to a negative infinity. And we said that we increase quickly at first from negative infinity, then slowing down until the point where at 180 degrees, we again have a length of that edge of 0. So we're going to quickly at first increase, slowing down until at 180 degrees we have a value of 0. Continuing on from 180 degrees, we saw that again the length of our tangent line is going to increase. And we saw this because in this quadrant, cosine is negative, sine is negative. That means a negative divided by a negative gives us a positive. And a positive value, of course, means that we are going to continue to increase in tangent, slowly at first, then more and more and more quickly, until once again we hit infinity at 270 degrees this time. So at 270 degrees, we hit infinity. So we're increasing slowly at first, then more and more and more quickly until we fly off up towards infinity. As we pass 270 degrees, we are going to, if you notice in this quadrant, sine of theta is negative, cos of theta is positive, negative over positive is negative, so we've now jumped again to negative infinity. And as we increase round to 360 degrees or 2 pi, we're going to increase from negative infinity quickly at first, then slowly, until we reach a value of 0 again. So we're going to increase from negative infinity quickly, then slowly, until we reach a value of 0. And you'll notice that our tan of theta is actually periodic over 180 degrees. So over 180 degrees we actually repeat. And we can see this if I was to plot again. So this would be about 90, this would be about 180, 270. So this is minus 360, minus 180. We'd see that again at about a negative 90, well exactly negative 90 rather, we'd have another of these dotted lines. And at negative 270 we'd have another of these dotted lines. And our tan would again, something like so, and again here, slowing down, passing through 0, then slowly again, and this last bit would look something like so we can see we are indeed periodic over 180 degrees. Once again, unlike sine and cosine, our maximum value is infinity, our minimum value is minus infinity. We know, of course, sine and cosine have a maximum value of 1, minimum value of negative 1. But that's all there is to tangent. Tan of theta is simply defined as the sine of theta over the cosine of theta. Sine of theta again is defined as the y-coordinate of the point on the unit circle. Cosine of theta is defined as the x-coordinate of a point on the unit circle for a given rotation from the x-axis in the anti-clockwise direction. Now, as with the previous video, there's really nothing to test here. There's no questions really to set. It's just a lot of theory. So I'm not going to be setting any questions in this video. But in the next video, we're going to see another way that sine, cosine, and tangent can be defined. And that actually allows us to relate these three trigonometric functions, which so far, they're pretty cool, and they have some nice graphs, and they have some nice relationships to the unit circle. But so far, they haven't really proved very useful to us. Well, by defining relationships between these functions and the angles of this and sides of a triangle, which is what we're going to do in the next video, that's actually where trigonometry starts to become extremely useful to us. But we'll see that in the next video. We've concluded this video here, so that's going to wrap up everything I wanted to cover at the moment. And with that, thank you very much for watching, and I hope you enjoyed this video.